Hello everyone, welcome to our presentation on mathematicology and proving them. In this video, we will first dive into chapter 2, logic, where we will learn how to reason carefully using statements, prove value and logical connect. Then we will move on to chapter 3, proving techniques, where we will demonstrate how mathematicians prove statements using different methods like direct, contradiction and in-product induction. Along the way, we will show examples to make these ideas easier to understand. And by the end of this video, you will see why logic and proofs are essential tools for solving mathematical problems.
Chapter 2, Logic. I'll be explaining about laws of logic. The laws of logic are basic principles that guide correct reasoning and logical thinking. They help us analyze statements and arguments clearly and determine whether a conclusion is valid. Understanding these laws is important in mathematics, problem solving, and making rational decisions in everyday life. In law of logic, we have 12 rules, which are double negation law, De Morgan's law, commutative law, associative law, distributive law, idempotent, inverse law, identity law, domination law, definition of implication, definition of biconditional, and also absorption law. Now let's move on to examples. The first one is in bracket negation P and R implies negation P. We will use definition of implication. We will get negation in bracket negation P and R or negation P. And then we will expand it using De Morgan's law. We will get P or negation R or negation P. And then we will put the P and negation P in one bracket. We will use associative law. We will get negation P or P or negation R. And then P or negation P, we will get tautology. So that is inverse law. We will get tautology or negation R. And lastly, we will use dominant law. We will get tautology. Question number 2. Using the laws of logic shows that R or in bracket R and P or negation R or S is a tautology. First, we will use absorption law at R or R and P. We will get R or negation R or S. And then we will put R or negation R together because we use associative law. And then we will get tautology from R or negation R using inverse law. And then lastly, we will get tautology using dominant law. Question number 3. State the steps and reason using the laws of logic with a final answer in implication form. The question is in bracket P or Q and in bracket Q or in bracket negation S or in bracket R and negation R. First, we will use inverse law. We will get P or Q and Q or negation S or F naught. And then we will use identity law. We will get P or Q and Q or negation S. And then we will use distributive law. We will get Q or P or negation S. And then we will change them to implication form. We will get negation Q implies P and negation S.
Truth tables are commonly used to determine the validity of logical argument. However, when an argument involves more than 3 propositions, the number of rows in the truth table increases rapidly, making it impractical. To overcome this problem, a set of logical techniques known as rule of inference was developed. This rule allows a valid conclusion to be drawn from given premises without constructing large truth tables. So for content, we have modus ponens, law of syllogism, modus tollens, rule of conjunction, disjunctive syllogism, conjunctive simplification, disjunctive amplification, and last one is rule of contradiction.
So for the first example, we have P implies Q, negation R implies negation Q, negation R and negation S, and the conclusion is negation P. So first we will have to write all the premises, and from number 3 we will be using simplification and we will get negation R. And from number 2 and 4 we will be using modus ponens and we will get negation Q. And from number 1 and 5 we will be using modus tollens and we will get the negation P. So the argument is valid. So for example 2, we have negation P and Q. R implies P, negation R implies negation S or T, and the conclusion is T. So first we will have to write all the premises, and from number 1 we will be using simplification and we will get negation P. And from number 2 and 5 we will be using modus tollens and we got negation R. And from number 3 and 6 we using modus ponens and we get negation S. And from number 4 and 7 we will using disjunctive syllogism and we will get T. So the argument is valid. So for example 3, we have P implies Q or R, S implies negation Q, P and S. So the conclusion is S implies R. So first we will have to write all the premises, and from number 3 we will be using simplification and we got P. And from 1 and 4 we will using modus ponens and we got Q or R. And from number 5 we're using implication and we got negation Q implies R. And from number 2 and 6 we using syllogism and we got S implies R. So the conclusion is the same and the argument is valid.
Chapter 3, Proof. In Chapter 3, we have proving techniques. In proving techniques, we have the forward-backward method, the construction method, specialization, the contradict method, contrapositive method, and mathematical induction. Definition forward-backward method. The forward-backward method is a proving strategy in which reason forward from the given assumption and backward from the conclusion to be proven, then connect both logically to complete the proof. The forward-backward method, we have to prove if A then B is true, assume that A is true and use this to show that B is true. A is hypothesis and B is conclusion. In attempting to figure out how to reach the conclusion that B is true, we will go through a backward process. When we make specific use to the information contained in A, we will go through a forward process and we can get a proof. Question 1. Prove that if XYZ is an isosceles right triangle, then the hypotenuse is square root of 2 times as long as of the leg. Analysis of proof for this question is hypothesis A is XYZ is an isosceles right triangle. Conclusion B, the hypotenuse is square root of 2 times as long as of the leg. Solution for this question is given triangle XYZ. A is triangle XYZ is an isosceles right triangle. This means that two of these sides are equal in length. For B, the triangle is also right triangle and the hypotenuse is longer than the leg. A1 is since the triangle is an isosceles, the two equal sides are X and Y. Therefore, X is equal Y. For A2, using Pythagoras theorem, we know that in any right triangle, x squared plus y squared equals to z squared. For A3, because x is equal y, we have to substitute y with x squared plus x squared equals to z squared. For A4, adding the term given, 2x squared equals to z squared. A5, taking the square root of both sides, z is equal to square root of 2x. B1, D is match the given statement that the hypotenuse is square root of 2 times the length of the leg. So, the solution is proven.
So now, this is another example for forward-backward methods. We can see the statement, which is a student is allowed to write the final exam if and only if the student has a valid hall ticket. So we use the forward directions, which is if a student is allowed to write the final exam, then the student has a valid hall ticket. From the forward direction, we get that exam rules require a hall ticket. Now, from the backward directions, if a student has a valid hall ticket, then the student is allowed to write the final exam. So, from the backward direction, we get that a hall ticket grants permission. As a conclusion, since both directions are true, which is allowed to write exam and has hall ticket, so the forward-backward method is proof.
Specialization method. If hypothesis A contains the quantifier for all, we use the specialization method. Form of A, for all objects with a certain property, something happen. To use this information, we specialize the universal statement to a specific object. They have a step of applied specialization. First, we have to assume A is a true and identify the object, the required property, and the conclusion something happened. 2. We have to choose one specific object, often obtained from backward reasoning. 3 is verify that this object satisfies the required property. 4. Conclude that the same result applies to this object. In short, specialized applies for all statements to one particular case.
Okay, for the example, we can see the statement for all real numbers x, if x more than 0, then x squared is more than 0. So, for the specialization, choose a specific value like x equals to 3. So, 3 is more than 0 is true, and 3 squared is equals to 9. So, it is more than 0 is true. So, the conclusion, the statement holds for this specific case. Okay, another example for specialization method is statement proof that 7 square is more than 0. So, given if x more than 0, then x square is more than 0. So, we prove it by first, from the universal statement, specialize to x equals to 7. So, 7 is more than 0. Then, 7 square is more than 0. Second, since 7 is more than 0, conclude that 7 square is more than 0. So, it is proof that a specialization method is used. So now, we move to contrapositive methods. For the conditional statement, we use if P, then Q. And the contrapositive will be if not Q, then not P. A statement and its contrapositive are logically equivalent. Why we use it? It is because it is often easier than direct proof, and it is useful when Q is simpler to analyze than P. How is it work? First, we identify the hypothesis and conclusion. Second, negate both and reverse them.
and third, we prove it. As the example, if a number is divisible by 4, then it is even. Now, we identify which is hypothesis and which is conclusion. As we know, number is divisible by 4 is hypothesis and it is even is conclusions. Second, we negate both and we reverse them, which is we negate a divisible by 4 by not divisible by 4, and it is even will be negate and it will be not evens. So we reverse them. So it will be the contrapositive method will be, if a number is not even, then it is not divisible by 4. So the key point is proving the contrapositive proves the original statement. So now we move. This is another example of contrapositive methods. We can see the statement, if a number is divisible by 6, then it is divisible by 3. The contrapositive will be, if a number is not divisible by 3, then it is not divisible by 6. We use the step I have explained just now, which is first we analyze which one is the hypothesis and which one is conclusion, which is the hypothesis is number is divisible by 6 and the conclusion is it is divisible by 3, and we negate it and we reverse it. So if we negate, if a number not divisible by 6, then it is not divisible by 3. Now we reverse it. If a number is not divisible by 3, so then it is not divisible by 6. As a proof of contrapositive, assume the number is not divisible by 3. Since 6 equals to 2 times 3, any number divisible by 6 must be divisible by 3. Therefore, the number cannot be divisible by 6. Hence, the contrapositive is true. So, the original statement is true. So now, we can see another example for contrapositive methods. So, the original statement is, if a student attends all class, then the student pass the exams. Now, we identify which one is conclusion, which one is hypothesis and which one is conclusions. So we know that the hypothesis is the student attends all class and the conclusion is the student pass the exams. So to make it contrapositive statements, we need to negate and we need to reverse the statements. So after we negate, it will be, if the student did not attend all class, then a student does not pass the exams. So after we negate, we need to reverse the statement. So the contrapositive statements will be, if a student does not pass the exam, then the student did not attend all class.
To summarize, in this video we explored mathematical logic and proving techniques, two fundamental pillars of mathematics. In Chapter 2, Logic, we learned how to reason carefully using proposition, proof value, and logical connecting. We also saw examples of truth table, logical equivalence, and everyday applications of logic. In Chapter 3, Proving Techniques, we discovered how mathematicians use direct proof by contradiction, and induction to verify statements rigorously. The examples show us that proofs are not just abstract. They are a way of thinking that ensures conclusions are reliable and precise. Understanding this concept not only strengthens our problem-solving skills, but also prepares us for more advanced mathematics. We hope this video has made logic fun and proof clear, interesting and fun. Thank you for watching. Bye! To summarize, in this video we explain